Cyclopropane represents the smallest possible cyclic alkane that we can have. It contains 3 carbons and 6 hydrogens, and it represents a very highly strained molecule, lots of energy. And one of the things that becomes apparent to us as we look at this structure in just the 2 dimensions that I drew is that we have approximately 60-degree angles here, and that creates an awful lot of angle strain because these tetrahedral carbons, these sp3 hybridized carbons prefer tetrahedral angles. So angle strain is a big problem for this molecule. The other place where we see a lot of strain energy in this molecule is torsional strain. If we take a look at the video as we rotate this around, I'll pause it right here, and you'll see that there's a significant amount of overlap between the sigma bonds here and here. Now, this video doesn't rotate this completely around 360 degrees, but there are 3 torsional strain interactions on the top and 3 on the bottom, and so that adds up to quite a bit. Between angle strain and torsional strain, we have a total strain energy of 115 kilojoules per mole. That's a lot. Here's cyclobutane, and when you look at this molecule in this dimension, you might guess that those angles are 90 degrees. So, of course, we have a lot of angle strain again because we have sp3 hydrogens trying to maintain tetrahedral angles. But I'm going to tell you in a little bit that those angles are smaller than 90 degrees. Let's go ahead and start this video, and you'll see this turn. And you can see a couple things. First, the molecule is puckered, but then also, as we continue, you can probably tell that these sigma bonds are not fully aligned with each other. These hydrogen-carbon sigma bonds with the ones in the back. So the molecule actually puckers and increases the angle strain. So the angles are more like 88 degrees. But the purpose of that is to relieve that torsional strain. So we still have torsional strain. Still lots of energy here. And the total energy here is 110 kilojoules per mole. A little bit less than our prior cyclopropane. When we add another carbon to create cyclopentane, we see the same sort of trend. We have a decrease in the angles from the expected 120 degrees so that we can have a misalignment of those CH bonds, so we reduce the torsional strain. So we do have a little bit of this angle strain here, and of course a little bit of torsional strain, and our total strain value has been reduced to 26 kilojoules per mole, so this is significantly less. So the more and more atoms we're adding, we can see the less strain on the molecule. And now we come to the star of the show. This is our cyclohexane ring, and we'll rotate this until we get a good Newman projection. Stop right there, and you can probably tell that we've got some really good dihedral angles here. This looks like 60-degree dihedral angles between all these sigma bonds, and so we have no torsional strain in this molecule. In addition, the angles are pretty close to tetrahedral. We're at about 111.5 degrees, so let's just say about 112 degree angles, and so our angle strain is reduced significantly. In fact, relative to the 3, 4, and 5 membered ring, we have essentially 0 strain energy in this molecule. Another thing to point out here is that this molecule, though it has 12 hydrogens, there are 6 hydrogens on the top side of the 6-membered ring. If we draw this plane right through the center of the molecule, we have 6 hydrogens that are on the top side of the ring. So we'll identify this as 1, 2, 3, 4, 5, 6. And on the bottom side of this plane, we have 1, 2, 3, 4, 5, and the 6th one is behind this carbon. It's hiding, can't see it. So there are 6 hydrogens on the top side of the ring and 6 hydrogens on the bottom side of the ring. The most stable conformation for the cyclohexane is known as a chair conformation. There are 6 hydrogens on the top side of the ring and 6 on the bottom side of the ring, as we'd indicated. But we can separate those into 2 different types of hydrogen atoms because of their geometries with respect to the ring system. So we have 2 types. One is called axial hydrogens, and those are the ones that are pointing straight up or straight down. You can see there are 3 axials pointing up and 3 axials pointing down. And then if we switch colors here, we'll go to describe the other set. These are known as equatorial hydrogens. And the equatorial hydrogens are on the perimeter. So this one here, here, and there. If we go over to the upper right structure, maybe we can circle those. The axial ones are the ones here, pointing straight up. There's 3 on the top, and there's 3 axials on the down side of the ring. Then we have 3 equatorial on the top of the ring. This one's pointed upwards, this one's on the upward side of the ring, and this one's on the top side of the ring. And then we have these that are on the down side of the ring, here, here, and there. At room temperature, and when only hydrogens are attached to these 6-membered rings, these molecules undergo what's known as a chair flip. Each of the structures on the energy diagram up here on the far left and on the far right have equal energies. As you can see, we rotate the dihedral angles throughout the energy profile here to come up with the molecule on either side of the diagram, where both of them are known as chair conformations, but you can see that the chair has been inverted. The bottom structures show us that same inversion. If we look at the carbon skeleton, we can see that carbon 4 has now been pushed up, and carbon 1 has now been pushed down, and that results in this inversion. Another really cool observation here is that all of the axial hydrogens, which on our left structure are these red arrowheads, have been moved into the equatorial position. Vice versa, the equatorial atoms on the left, which are these blue dots, are now in the axial position on the right structure. The best way to visualize one of these chair flips is to do it yourself. So I built a cyclohexane here with 3 red atoms axial up, 3 red axial hydrogens down. And now to do this chair flip, you want to grab the carbons on either side of the ring, on opposite sides. The one that's pointing down, which is this one, I'm going to lift up. And then the one that's pointing up, I'm going to push down. Then if I grab the 3 white hydrogens on the top and bottom and I straighten my structure, I have a new chair conformation. And you see all red atoms have become equatorial. To do the opposite, we'll go ahead and grab those carbons again, and I'll take this one here now and lift it back up. This one, move it back down. Then I'll grab my red atoms and kind of re-straighten this, and there's my chair again with my red atoms all axial. Now the next step is to try to draw this chair flip. So go ahead and grab a piece of paper and we'll see what we can do. The first thing to become comfortable with is drawing the carbon skeleton of the cyclohexane in its chair conformation. So let's see, let me draw one here, and then we'll talk about how this is made. Okay, so in this case, I drew the back part of the cyclohexane first, and then I drew this front part here. And you can use whatever pen strokes you think is best. I drew these 3 lines first, and then I'd get this one, and then I came this direction. Not really sure why I did it that way, just habit, I suppose. So my pen strokes were to draw the top of this ring first, or actually in 3 dimensions. This is the back of the cyclohexane ring. We're looking at bond 1, 2, and 3, and then I did 4, 5, and 6 to close the ring off. Notice that bonds 1 and 6 are parallel. Bonds 2 and 5 are parallel, and 4 and 3 are parallel. Let's go ahead and try drawing this again beneath the first one that we did. The first angle for bond 1 I'm going to draw is going to be a fairly steep angle upward, and then 2 and 3 are a little bit more shallow angles. And then as I come up with 4, I stop, and then I make sure I'm going to go parallel with 2, and then close that ring system off. Sometimes the slower I do the chair, the worse it looks. Let's try drawing the ring flip version. We'll put in some equilibrium arrows here. This time, I usually draw the bottom of the 6-membered ring first, or that which would be facing you. So I'm going to come down at a steep angle, and then go up, down, a little more shallow, and and then I'll come down, make sure this next bond is parallel, and close this six-membered ring. Well, it's not quite as nice. So I did this bond, here's 2 and 3, then I came back and did 4, 5, and 6. And like before, what should be true is that bonds 1 and 6 should be parallel, 4 and 3 should be parallel, and 2 and 5 should be parallel. Let's go ahead and try that again. We'll come down here. So down, up, down, down, up, down. Oh, not too bad. Next, we've got to learn how to draw our hydrogens in place. And that's actually a little bit easier once you've got the six-membered ring in place. So let's make some space on this page. Notice the positions here that I'm highlighting have carbon positions that are pointing in the upward direction. At that position, we're going to have axial hydrogens that are up. And if you can identify these three positions here as carbons that are pointing downward, we're going to have axial positions pointing down. Drawing in the equatorial hydrogens is a little bit complicated because it's a very common mistake to draw 90-degree angles, for example, like this. Now keep in mind, these carbons are sp3 hybridized, so they don't want these 90-degree angles here. They're looking for more angles that represent tetrahedral positions. So let me go ahead and delete those hydrogens. So on the carbon here on this right side again, that means that the hydrogen is going to be down at an angle. And now we've got approximately a tetrahedral angle. And as we come down to this position here, my hydrogen is going to be up at an angle. And there's that tetrahedral angle right there. And we'll repeat this as we go around the ring. This hydrogen is down facing, this one is up, this one is down, this one is up. Note that each carbon atom has an up and a down position. The axials aren't always in the upward position, and the equatorials aren't always in the down position. For example, here, this axial is down, and this hydrogen is up. And let's go over to the other ring now. From the video, you probably remember that by doing this ring flip, we took this carbon here, and we pushed it upward, and then we took this carbon here, and pushed it downward. And as that molecule came back into a chair conformation, we noticed that all of the axial positions became equatorial. All of the equatorial positions became axial. So this hydrogen here that I'm circling is going to be on this carbon here. Maybe it would be helpful if I number these atoms, these carbon atoms. 2, 3, 4, 5, and 6. So this is 1, 2, 3, 4, 5, and 6. So those equatorial hydrogens on the left structure, on positions 1, 3, and 5, now become axial on positions 1, 3, and 5. And those that were axial on position 2, 4, and 6 that are pointing up will now be down on 2, 4, and 6. And our equatorial positions are going to be here in red because we're switching those positions. And again, you want to make sure that you're maintaining angles greater than 90 degrees.